Okay, so theoretically it's recording right now. And if I go into full screen mode. Oh, there we go. All right, so this is static electricity. That's the first topic that we're going to do in electricity and magnetism. Static electricity is, what do you guys know it as? It's the most common. Balloon, okay. No, I wasn't expecting that one, but yeah. What else? Where do you guys witness static electricity the most commonly? Yeah, exactly. When you what's that? Friction. Friction, yeah, when there's friction and you generate some charge and then you discharge it or you charge yourself through contact with something. Do you guys know what a ground is? A ground. Sure, and the ground is a ground, but in electricity terms, a ground is something where the electrons want to go to. All right, so if I touch you and I give you a shock, technically you're the ground because my electrons are trying to get towards you, and then you're going to discharge the electrons into the actual ground because the ground is a better ground. Okay. There are ways of charging objects. We're going to look at that and all that stuff. What's a really big example of static electricity? Like we have tiny little shocks, and we have thunder, lightning. Yeah, lightning. That's a huge static electric shock that goes from the clouds to the ground. It has to do with water molecules. We'll talk a little bit about it. But it's the same principle. You rub your feet on the carpet, you touch your buddy, you give him a shock. All right? The clouds rub up against each other, get close to the ground, gives the ground a shock. All right? Essentially the same situation. All right, so let's move forward. Next slide. Okay, so the learning objectives for today are to analyze the situations in physics associated with static electricity and to describe different instances of static electricity, or how it's applicable. One thing that's really important for science in this school, in this course, in your whole life, it's doing that flip thing again. Eh? One thing that's really important is for you guys to be able to apply what you're learning. All right, so if you ever feel like I'm just teaching you just abstract concepts, like, sir, why are we doing this? Ask me and I'll try to explain it to you. I'll try to give you an example of why it's important. Okay, it's super, super, super important that you guys know that. And I'll have questions on tests and exams asking you guys to apply them in real world situations. Okay, so try to put that into context. There is a history of all this stuff. This whole concept started with a guy named Cavendish who described what static electricity was. And then there's this whole series of events that happen afterwards that lead us to where we are today. We use concepts of electricity and static electricity even in your devices. Do you guys have a flash in your cameras? That's static electricity. We're going to talk about that. It has to do with capacitors and charge movements and all that stuff. I'm not going to explain these now because we're going to explain them all later anyways. Okay? So what is static electricity? Why is it? What can you infer from it? What do you guys think? I'm going to make the awkward pause here and wait for you guys to put up your hand. Yeah.
It's caused by friction.
Caused by friction? Only or one way? It can be caused by friction. I like the way you say that. Okay. What else? Yeah. Electrons move from where to where? One surface to another, okay. Let me ask you a question. The term static electricity, what terms do you find in there? Static, what does static mean? Doesn't move, yeah. So this one's the opposite of movement. What is an example of electrons that do move? What kind of electricity and stuff do you guys know where it involves movement of charges? The opposite of static electricity, or dynamic electricity. Awkward pause. Yeah, circuits. All right. So circuits would be the opposite of static electricity. Let's write that down. So we're going to write down it's a situation where charges don't move. All right. Situations where charges don't move. What is this? I'm going to have to erase this later, but it's okay. Our charges don't move. Come on, guys. There we go. Does not involve moving charges. Moving charges would be something called circuits. We're going to learn about those. You'll get sick of those at some point this year. Any questions about that? All right, so let me just erase this. Static electricity occurs when there is a buildup of charges. All right, so it's not that the charges move, it's that the charges build up somewhere. Okay? And the charges are building up. They might move afterwards, but that's not what we're referring to at that point. Okay? It's called static because the charges don't move. Okay, we're good? And the stuff that you guys deal with, these electronic stuff that you have, and what I'm using in my hand, and this pen uses a battery called a quadruple A battery. Have you guys ever heard of that? You guys ever heard double A, triple A? Quadruple A is one that fits in here. I thought it was interesting. Ends up being really expensive. All right, so the electricity that we use every day involves moving electrons. Have you guys ever heard of coulombs and all that stuff, right? So at this point, this is all review. 1 coulomb is equal to 6.2 times 10 to the 18 charges. I'm not so sure I'm going to ask you guys to memorize that. Ask me later when it comes to a test. Maybe write down for now. Ask teacher afterwards if we should memorize this. I don't think so, because we're going to use it anyways so much that you guys are going to remember it. Maybe not so much the first number, but the second number. All right? So it doesn't matter how many charges we're talking about. We're talking about what is the value of a single charge. And when I talk about an electron, or when I talk about a proton, right? You guys know what those are? Yeah? Okay. When you talk about an electron or a proton, one single one of those charges will have a charge of, in a situation of an electron, negative 1.6 times 10 to the 19. What is a charge of a proton? To the minus 19. What are the units? Coulombs, yeah, exactly. So the only difference between a proton and an electron is the value of the positive or the negative in front of it. Okay? Any questions about that? So if you have one proton and next to a one electron, essentially next to each other, what's the overall charge? 0. Yeah, absolutely. Okay, so they add like that. Is it a vector? Do you guys remember what vectors are? Yeah? Is this a vector? No, not a vector. Even though it's got a positive and a negative in front of it, it doesn't mean it's a vector. Okay? Not because there's not a movement, because there's no direction. Yeah, there's no direction. Yeah. All right. One charge, one electron, one proton, we call that an elementary charge. All right, so that's the definition that I have at the bottom there. All right, that's just one charge. It's not 1 coulomb, it's one charge. Okay? So if I ask you, what is the charge of an elementary charge, what would you say? Say it. I hear someone whispering, and you might as well just say it out loud. In coulombs. I'm asking for one charge. You're telling me for many charges. You can ask me, I'm asking you, what is the charge of an elementary charge in coulombs? Nope. Yeah, minus 1.6 times 10 to the negative 19 coulombs. No, it's going to ask me to reconnect again. Ah la la. This is more complicated than I thought. Oh no, it's working. Okay, perfect. So far so good? If I were to ask you a question, let's go to the next slide. A balloon holds 8 or positive 8 microcoulomb. You guys know what micro is? Yeah? What is it? 10 to the minus 6, yeah. So a balloon holds 8 times 10 to the minus 6 coulombs of charge. How many protons are there? Just do a quick calculation. Let me know what you get. Oh, come on. Someone have an answer for me? To the power of 13? 13? 13? Yeah, and what's the unit? What am I asking for? So is it how many protons? Yeah. So 3.1 times 10 to the 13 protons. Okay? That's a lot of protons, right? It's actually not so much because it's in microcoulombs. Yeah, sure. Okay, so the way I did it was I said that I'm trying to figure out how many protons are 8 times 10 to the negative 6 coulombs. So that's this question mark, this X here. I don't know why there's a cross over it. Oh, come on. Still trying to learn this, all right, guys? All right, so I want to try to figure out how many charges that is. So I know, what I know for sure is that 1.6 times 10 to the negative 19, that's equal to 1 proton. This is what I know. This is a universal knowledge kind of thing. You guys need to know that now. So if I set up a proportion, it's just cross multiplication. So that times that divided by that is going to give me that, right? You guys remember how to do that? Yeah? It's kind of like a unit conversion. Think of it that way, okay? So you can describe a charge as a function of protons, or you can describe a charge in coulombs, right? And the positive and the negative just telling you if it's electrons or protons. It's good? Can I move on? All right. So complete these two sentences. Most objects that do not contain charges are referred to as I hear the answer, I just can't hear you, what you're saying. I hear some talking. All right, awkward silence. You can say it in French if you know the answer in French. Neutral, absolutely. Yep. It's first day of class, guys. It's easy stuff at the beginning. The hard stuff will come afterwards. This means that what? What does it mean that something is neutral? Say that? Doesn't have any charge, or the sum of the charges is equal to 0. That's very good. Another way of saying that is what? Yeah? Exactly. It means that the number of protons is equal to the number of, come on, let's go back, electrons. That's the same thing as saying the sum of the charges is 0. That's the same thing. It's both good. All right. If you have a deficit of it, this is easier now. Come on, you guys got this. If you have a deficit of electrons, what are you considered to be? Positive or positively charged. Good. If you can't read my handwriting, let me know and I'll try to be more legible. I'll try. Ah, come on, this thing is so sensitive. All right. And conversely, if you have electrons or extra electrons, you are? Yeah, very good. Negatively charged. I put a point at the end of my sentence and it switches slides. Okay. By the way, all our classes are 2.5 hours. How many breaks do you want in that time? 2? 2 is good with you guys? Okay. Moving on. This, we haven't really talked about it yet, but it's common sense. So we're going to talk about it right now. If you don't know it, it's no problem. It just, if you don't know it after we talk about it, then it's a problem. So you have two oppositely charged particles. What can you say about them?
They are attracted.
Yeah, absolutely. They attract each other. So opposite charges attract each other. Okay? You guys know, okay, this is now enrichment, all right? It's not enrichment. Everyone needs to know this, but I would be surprised if you knew this. I would be impressed if you knew this. Why are they attracted? What is the thing that makes them attracted to each other? Their what? Their affinity, but what's that affinity? You're maybe not using the right word? That's a good guess. It's not the right answer, but it's a good guess. Yeah.
I don't know.
You want to give it a try?
Okay, well, maybe they want to exchange an electron, so put one electron wants to...
Kind of like protons, where one proton... Okay, that's more a chemistry answer, but not relevant in this case. Where there's a proton, like a proton donor and a proton receiver. No, not so much. What happens in space between two massive objects? They collide? There's a gravitational force. There's a gravitational force between those two objects, right? That means between two oppositely charged particles, if they're attracting, what does there need to be? It's not called a nuclear force, but it's a force, all right? That's what I'm looking for. There's a force between these two things. It's not a magnetic force, but it's close to that. Those are magnets. So when we're talking about poles, we're talking about magnets, and that's magnetic force. So we have magnetic force, which you guys are great with. What is it called? Electric force? Close. Electrostatic force. All right? Should I write that here? This is referred to as, yeah, let's call it electrostatic attraction. Okay? This is going to drive me nuts. Electrostatic attraction. If you had two similarly charged particles, what would happen? Yeah, they would be repulsed, exactly. And what would you call it in that case? Electrostatic repulsion, absolutely. Okay, we're going to do an experiment on this. This is called Coulomb's law, and we're going to do an experiment on this on Tuesday. You guys are Tuesday class, right? So next Tuesday we're going to have a lab on that. It's going to be, I'm sorry, the most frustrating lab because it's so finicky. I was at an hour this morning trying to get things to push each other. Anyways, it's going to be your problem next Tuesday, but it's otherwise very straightforward. Okay? So static electricity, it is the imbalance of positive and negative charges that cause balloons to stick to walls, for example. All right? For your hair to stand up when you brush your hair on a dry day. I don't have that problem. On the static shock you receive from a door handle, that's all static electricity. Okay? Now, we're going to get into the more complicated stuff here now, okay? So there's something called the triboelectric series. Do you not have this slide because I added it literally 5 minutes before giving you this presentation? I'll update it later. You'll have it with my notes when we do the class and all that. So triboelectric series determines what receives electrons and what receives protons. So you guys all have heard of this famous thing here. You guys talked about it at the beginning of class. This is a balloon. May I borrow someone's head? Head. And preferably if you have long hair. So you and I, we don't care. Someone with long hair. I'm going to just, yeah, okay, you come. Actually, I don't. All right, so the balloon is, you're the closest, right? So is the chair getting attracted to the balloon right now? Not really. Okay, but I'm going to rub it. All right, is that balloon attracted to his hair? Yes? Attracted? All right. All right, and right now, what is his hair doing? Is it going back to normal? Yeah, I mean, there's something going on. What's going on? You guys, you call me here. What's going on? Yeah. Yeah, you're right. So between the hair strands, there is repulsion. If there is repulsion, that means what? That they're the same charges, all right? What were they before I rubbed it? Opposite? Opposite? Neutral. It was neutral. And then something happened, and then they became similarly charged. So what happened? Yeah, it's the phenomenon of static electricity. You're about to say exchange of, just that, the word exchange is good. So let's try to improve it. All right? There's an exchange of something. What's being exchanged? Electrons and protons, all right? In general, we don't like to say that protons move. Why don't we like to say that? I hear right words. Who said nucleus? You did? Yeah, how about? So explain it. Yeah, it would destroy the nucleus, or it would do what? Let's think more chemistry first. I mean, I hate to say it, but chemistry is very important. Exactly. First of all, most of physics? Yeah. Physics, right? Okay, so if you physics is made up of carbon, which is, I mean, hair is protein. You guys remember what proteins have the most atoms? Which atoms are make up proteins mostly? Carbon, nitrogen, oxygen, other stuff. Okay, you guys got the main ones. Carbon, nitrogen, oxygen. And hydrogen, of course. His hair is made of that. After I rubbed it, did I change the composition of his hair? No. So if I remove protons from his hair, what happens if I remove a proton from carbon? What's going to happen? I'm changing the atom, right? That's something that's nuclear, the opposite nuclear fusion. I don't know which term is that. But it's, yeah, if I were to take off a proton, I'd be changing the atomic composition, and therefore it wouldn't be made of carbon anymore, therefore it wouldn't be hair anymore. I'm not doing that to his hair. So what's the thing that's going to be moving? Electrons, right? Because you can have charged particles. You have carbon that's positively charged, carbon that's negatively charged, so it's carbon. But you can have both charges of those atoms. So which one is which? Where is the electrons going? Is the electron going from the balloon to his hair, or his hair to the balloon? Hair to the balloon. Why? Because of the charge. Yes, absolutely. Okay. So there is this chart that helps us with this. Okay. And if you were to ask me what property it has to do with, I don't know the answer to that. Right? I don't know why this chart is the way it is. But we follow this chart because that's how we know where the electrons go. All right, so I rubbed Felix's hair with the balloon. Tell me what's happening with the charge. Am I getting your name right? I feel like I'm not.
It's not.
It's not. Okay, so what did you? Okay, so what did you? Yeah. Okay, sorry about that. Who is Felix? Felix. Okay, sorry about that. So yeah, so where are the electrons in Yael's hair going here? You guys said it's going here. And then what's happening? Tell me what's happening. Why is it that his hair gets attracted to the balloon? And tell me why his hair is repulsed from each other.
Because my hair are positively charged and it's
Okay, so the electrons went here, all right, and therefore your hair becomes positive, and now this is negative. Before I rubbed it, what was the charge of this? And you charge of your hair? Probably neutral. Yeah, I mean it depends on the humidity in the air sometimes. Everyone have a bad hair day? I have them all the time. That's because of the humidity in the air. Right? So the humidity in the air makes it so that your hair does things that you don't want it to do. They repulse and attract and whatever, and so you have bad hair day. So exactly, so you have that, and the hair is going to get the positively charged hair is going to get attracted to the negatively charged balloon. Why are his hairs being repulsed from each other? Because they're the same charge, exactly. So now all of his hair strands are positively charged. And if they're positively charged, they repel each other. Good? Let's write that down. So this is the one I'm talking about. That was our first demo. Take a minute to summarize this in your own words. I'll write it down as well, but I prefer it if you wrote it in your own words, okay? You can talk to each other if you want to get the wording right, okay? I'm going to have to figure out this pen thing. It's annoying the crap out of me. Okay. So we can think about it in 3 different steps. Before, during the friction, and after the friction. And so you know that everything starts off neutral. Then after the friction, or during the friction, the electrons move from the hair to the balloon, creating a negatively charged balloon and a positively charged hair. Negative attracts positive, so the balloon attracts the hair, and the hairs repel each other. Okay? Right. Done with that. Oh, you want me to keep that up? Good. Okay, let's move on to the next demo. So the next one is with water and rod. I'm not going to actually do that. I'm actually going to put this here. Have you guys ever seen one of these before? This is called you guys know what this is called? Starts with a V, it's got a Dutch name. Van de Graaff generator.
That's what I'm gonna say.
Yeah, Van de Graaff generator. I can write this down later. The Van de Graaff generator is going to, who's ever played with one of these before? Yeah? People with long hair normally play with this. If I did it, they wouldn't say anything, except on my arms, actually. You want to try it? I don't know if you can see it from there, but you can see my arm here. Yeah, that's from being Middle Eastern. Anyways, all right. So, okay, so that's a Van de Graaff generator. It works through friction. It's actually like there's a belt that's going in and out. You guys see that? Oh, that's static electricity. That's because it's very humid today. That belt going up and down is creating a charge because it's going through friction. And what's going to happen if I, actually before I say that, if I bring back my table of triboelectric series, is this going to be positive or negatively charged if I touch it? I don't want it because it scares me.
Positive.
Positive, all right? Because it's higher up on the list. Okay? All right, so I'm going to touch it with this. And now what's the charge of this? Okay? They're both the same. Actually, you know what I should have? I'm going to go like this, and I'm going to turn it off. What's the charge of this? It's positive? Let's try. All right, this is the experiment. So I have a stream of water here. Does everyone see it? This pillar and that pillar. Leo, you're the only one who's affected by this on that side, but almost all of you are affected by it on this side. If I do this, nothing happens. Alright, so
Oh my god.
are you sarcastically saying that? It's almost
That wasn't sarcastic. It was exaggerated, but not sarcastic.
Ah, this sucks. It's not doing it well enough. Do I need more charge? I'm literally afraid for my life here. Anyone else want to do this? Alright. Okay, yeah. There you go. See that? So is it positively charged or negatively charged? And then now you're asking yourself, wait, water is charged? Because did I rub the water?
No.
No.
Well, the minerals in the water, no, it's not.
What do you guys know about water? What did you learn about it in chemistry class?
The hydrogen and oxygen.
It's 2 hydrogen, 1 oxygen. Sorry, yeah, 2 hydrogen, 1 oxygen. Yeah. It's polar. Yeah, super. That's the word I was looking for. What does it mean that it's polar? It's not charged. Exactly. Part of it is positive, part of it is negative. Which part of it is negative? Just say it. Oxygen. Yeah, oxygen is the positively charged part of it. And, sorry, the negatively charged part of it. And this is attracting the water or repelling the water?
Repelling water.
It's what? So if, let me try that again. Actually, instead of doing it this way, yeah, I want to need your hair here. It worked really well. Alright, perfect. Thank you. Like that. There you go. Alright. You can kind of see it, right? I just can't get a light enough stream for this to work. Try really carefully. You can kind of see it, right?
Yeah.
You can see the stream. So is it attracting or repelling?
Attracting.
Attracting. So that means if that is polar negative charged molecule, this must be positively charged, which means that this was positively charged. So what happened to the charges? So let's think of it. We have to think hard here. This is wet. All right. Ever feel like throwing with your left hand? It always feels a bit weird. Yeah.
You didn't say by motion we're going from the head to the balloon, so the balloon is negative, and I just said it was positive.
You're right. I did say that.
So the water
But you
is
said the water was positive because of the.
No, the water is negative. That's for sure. Unless, because there's 2 hydrogens. Let me look that up. I might be wrong about the water. I'll look it up. Okay. I need to write that. Thank you for that. Okay. What was I saying? All right. So So imagine that you have. We said what was this? Is that high on the triboelectric list? Is this high on the triboelectric list? Yes. So it's going to be positively charged. If I touch this with it, what's going to happen to this charge? First of all, let's say I didn't charge it, didn't touch it. So positively charged atoms or whatever are up here, right? It's a metal, so the protons could be on the surface. And if I get close to it, what's going to happen? If I just get close to it, I'm not touching it, what's happening to this? It's what? It's attracting it. Is this charged?
No.
It's not charged. Nothing? There is something. There's no contact, so there's no jumping of electrons. Although when you get somewhat close, it can jump through the water. You see that? About touching it? You can see a spark there. That's because there's humidity in the air and it's jumping through the water. But let's say there wasn't humidity in the air and I bring this close and there was no contact. What's happening to this? Let's make a drawing.
The dark balloon can be positive too.
Yeah. Exactly. Okay, so let's draw this. We have this Van de Graaff generator. Okay? And we're saying, or I'm telling you rather, that this is positively charged all around it. Okay, that's that. Come on. When I bring this other thing next to it, and this thing that I bring next to it is, you guys said neutral. So what's happening there? Is this, first of all, is this a conductor or an insulator, this thing? It's a conductor, which means that electrons can move freely in a conductor. That's what a conductor means. We'll talk more about that later.
The charges are all going to the same.
The charges are all going to the same place. So which charges are going where? The electrons are going where? Towards it. All right, so if I go like that, all right, oh, come on. All right, so the electrons are now focused on the left side. They're just moving over, all right? And the protons, they don't move, so the protons, they're all over the place. All right, the protons are all over the place. The electrons are located in one place. So if you were to, if I were to bring this close like this, what's the charge around here on this thing? Here? Negative. What would the charge be over here? Positive. Okay, if I were to touch this, what would happen? I would be the ground? Maybe not. So the ground requires electrons. So if I'm touching it here, what's the charge over here? Positive. And do positive charges move? No? So if I touch it, what's going to happen? It's going to take my electrons, my excess electrons, so let's say I was rubbing stuff or whatever, I gather electrons, if it happens, you can gather a positive charge or negative charge, but essentially whatever excess negative charge I have, zoom, goes into there. All right, that's if I touch it. And then I move it away. What is the overall charge of this? It's negative, because it never removed this, I never touched that thing. All right, so it's important whether I mention if I touched it or not. So I didn't touch it. It was neutral. It never lost its electrons. It never lost its protons. It got my electrons. So what is it? Negative. Okay, so that's not what I did before I touched it. So what does that mean? What's that? How is that different? So this thing is positively charged. And then this thing touches it. Oop, let's dry. So touch. Now we have this situation. I gotta figure that out so bad. All right. So what's going on? Yeah. Yes, so all of the electrons in here are going to move over into the big ball, into the Van de Graaff generator. And then I move it away. So now this thing has got all of its original positive charges. And, oh my God, come on. I feel like I'm just throwing this. Okay, so now it's got the negative charges from the rod that I was holding. And therefore this rod now is what? Positive, exactly. It lost its electrons, leaving it in a positive state. Okay? So now I have this positively charged thing. And I'm making it so. Okay, now we can determine what is water. So is water positive or negative? Negative, because it's attracted to something that we're sure is positive. All right, that means my balloon thing from before is wrong. So I'm going to write that down here. So does the balloon become positive or negative? Balloon positive or negative? Okay. So take the time, just like we did with the first demo, take the time to write down what you think happened here. I'll write it on the board because I'm tired of that tablet thing for now before I figure it out. So I'm going to write down on the board what's actually happening. I want you guys to do the same thing. Discuss it amongst yourselves if you're confused. stop. I want you guys to write it. Don't copy what I'm writing. Everyone done writing? I'm just going to try something. Okay, I'll figure it out later. Can someone show me your answer? Volunteers or points? I'm not going to ask Yael or Leo or anyone who's pretty extra. The participation is. Even if it's wrong, honestly, I don't care if it's wrong. Because if it's wrong, then the teacher's okay. How would you explain the whole phenomenon from when I touch this, brought it next to the water? Okay. Okay. Okay.
The water checks the blood because the water is negative, so
Absolutely. Very good. Can I ask you guys an extra question? Let's say, because I don't know if you guys noticed me doing this, this is on. What's the charge here? What's the charge here? Positive? What if I did this? What is the charge here now? Neutral. Yeah, very good. Very good. That's super important. Okay, this is now neutral. I didn't do anything because what had happened? This stopped being charged, and now what you said this was positively charged, so what is it going to do to its negative charges in there? It's just going to take them back. So right now this is not charged. Okay? So it's important that what do I need to do? If I want that to be charged, what do I need to do? Take it off, and then turn this off. Got it? Now this should theoretically be charged. Of course, it's not doing it. Let's do it again. Tanya and I spent like a lot of time this morning doing this. It is cool though. She was so scared. All right. It's not working now. I was working on this side, but it's a conductor. It should be equal. Hold on. One more time. This time I'm going to go super fast. I'll do the tip. All right. It worked better with the balloon, eh? Wonder why. Okay. We know what's supposed to happen. I'll figure it out. We'll explain it next time. There is 45 minutes left of class. Let's take a 5-minute break, and then we have one more demo, and then I want you guys to practice some problems. So, like I said, these two balls are hanging from a thread, and these balls are painted with conductive material. They're hanging from a wire which is conductive, and it's attached to this metal piece which is conductive, and there's a metal piece on top which is also conductive. So electrons can freely flow through those two balls, those string, the wires, this bar, and this ball. Okay? Everything else is insulated, and you can see that there's no charge here or whatever. Okay? So far so good? If I were to bring my machine, okay, now obviously it's not going to work today, because I'm unlucky today, but I'm going to try it anyways. If I had done the touch, this thing is positively charged. If it's positively charged and I bring it and touch this, what's going to happen? You want to try it? Explain it? Yeah, so the electron's going to go up and into this, and then that's going to remain and be what? Positive. And if they're positive, what do positive things do to other positive things? Repel. So those balls should actually, you should see them going apart from each other. Correct? What if I didn't touch it and I just brought it close? What would happen? Would it do the same thing? Yeah, exactly. The electrons would go up, leaving that bottom part to be positively charged and still repelling each other. So both situations, they should repel. Now, what's the difference though if I touch it or if I don't touch it? Yeah, what do you think?
Is that when you move the stick, the charges remain the same.
When I don't touch it or when I do touch it?
When you don't touch it.
Ah.
As you move it, the charges remain the same.
Ah, super good. Exactly what I was looking for. All right, so if I don't touch it and take it away, then the charges will go back to being normal and the balls will touch each other again. If I do touch it, now I can take this away because all the electrons are now in here, and these things will be permanently positively charged. It's going to last not even 1 second, but you'll see that it'll take longer for the balls to get back closer together if I do touch it. Okay? Again, if it works. This thing's on max. Okay. Alright, that wasn't supposed to take off. Alright. Charged. Man, I can feel my hair moving close to this thing. Alright. Thank you for bringing it close to this. Again, it's gonna suck for those of you in the back. Is it gonna work? Come on. Yeah, I need your hair again. That's because now at this point it's only been on your hair and I feel like oh, you can almost see it. You can see it? It's very faint. I'll have to troubleshoot this to get a more obvious response. Alright, but anyways, okay. No. Emily signed, so it's true, it passed. So the balls did kind of go apart. It wasn't perfect, but that's theoretically what's happened. Okay? So these things, these balls, we're going to your lab next week is about this kind of thing. These are called pith balls, P-I-T-H. And they should repel each other, and you should be able to, based on angle that they separate, or the distance from how they separate, you should be able to calculate the charge between them, which is pretty cool. That's what your lab is going to be on Tuesday. Let's write down what happened here. I'll give you guys 2 minutes to write it down. Write down what should have happened. Okay. I'll write it on the board as well. So that device there is called an electroscope. This thing here, that's the electroscope. That's what I was thinking. Just a warning, I'm going to ask you guys to volunteer your answer again. It's going to be different people. Who lives in residence? You're lucky. So Genevieve, I'm going to ask you, okay? In 2 minutes, I'll ask you. I'm going to ask, next class, just sit back where you are, just until I learn your names, okay? That's going to help. Literally raining sideways. Look at that thing. Oh. Okay. Yeah.
Okay, so the rod is positive, so when it touched the metal plate,
Yeah.
it attracted the electrons, which made both balls positive, so they.
Balls? Okay. Which part were you talking about? These balls or the balls?
What is it on?
Oh, okay, sorry, I wasn't following. So start again, sorry.
So the rod that was on the generator was positive, so that
Yeah.
when you touch it to the top of the electroscope, it attracts the electrons, so then the two balls inside both go positive, so then they would touch each other.
Perfect. Everyone understand that? Any questions? No? Okay. So I'm going to write what she wrote. What you guys are going to do now is you're going to go to the next couple of slides, and there's some questions. What I want you guys to work on, there's 2 sets, is the YouTube video. So skip 2 slides and go to the link that has the slide that has a YouTube video. Watch the YouTube video. What I want you guys to do is in every of the examples, try to explain what's happening. Exactly the way we're doing it right now. Doing it on your own. Work in groups of whoever's close to you. Discuss. I want you guys to talk about this, okay? So talking is a good thing. Do the video one. You can do the other one at home for homework. Not that I'll check it or anything, but...
Question. When you put the balloon on the electroscope, work then? Doesn't the balloon negatively charged?
I was wrong about that. It's positively charged.
Okay.
I don't know why though, because if you look at the, let's go back here. If you look at this, so we're going back to Yael's hair.
Yeah.
So this is more lower, closer to the negative end than human hair is. So theoretically, that should be negatively charged when you rub it on the hair. Actually, does that make sense?
Because the hair would give the electrons. No, the balloon would give the electrons from the hair.
The balloon would get the electrons from the hair, which is what we were saying before.
Get or give?
Will get, because
Yeah.
this has the tendency of becoming negative.
Okay.
That's what this means.
Okay.
All right, so it's closer to the negative end, which means that it's going to get the electrons.
Yeah.
And if that's the case, the hair is positively charged. Now, why did the balloon work and not this thing? And so this thing, let's say, is made up of some kind of metal, which is over here.
If you put a negatively charged object onto the electroscope, nothing would happen, right? Well, in
It would.
theory-
No, the same thing would happen.
thing would happen?
Yeah, because
Okay.
there's just the opposite charges would happen,
Yeah.
right? And then the balls would still be the same charge and it would still repel.
Yeah, so exactly
Right?
it works then.
Yeah, that would still work.
Okay.
But okay, so the reason why I understand. So the reason why we're questioning about the balloon is because it attracted the water,
Okay, yeah.
and the water is negatively charged or negatively charged. It's more negative than positive.
Okay.
So that means the balloon is positively charged. That's what didn't make sense.
Okay.
That's what they gotta figure that out.